I'm Dr. Justin Essery, an assistant professor at Rice University. The International Methods Colloquium is a periodic online interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Rice University and the National Science Foundation. This week's speaker is Jonathan Kropko from the University of Virginia with a talk entitled Beyond the Hazard Ratio, Generating Expected Durations from the Cox Proportional Hazards Model. Dr. Kropko's talk will last between, or should I say Mr. Kropko's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You may call in to ask a question on the air at our toll-free call-in line, 1-855-667-8287. That's 1-855-NO-STATS. You can email questions to us at methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question box that appears on the control panel on your screen. For our viewers outside the United States, we recommend you use the Ask Question box to ensure that we receive your questions immediately. A copy of this paper and slideshow that goes along with this presentation are available in the Handouts box in your GoToWebinar window, so you can follow along with the presentation. Now I'd like to welcome Dr. Kropko to the IMC. Welcome.
Thank you very much, Justin. Yeah, so at Virginia, I'd be called Mr. Kropko because Thomas Jefferson, the founder of the university, wasn't a doctor, and so people get called professor. They don't get called doctor. It's kind of a weird quirk of where I'm at. But anyway, I'm really happy to be here. This is my first ever internet talk. So I'm going to talk to my computer and hope that the words get through to all of you. My co-author Jeff Hardin at the University of Colorado at Boulder and we're both very excited about this project. We're hoping to just wrap up a few odds and ends and get it out to a journal really soon. We are excited about any feedback you might be able to give us on this project. So you know, we're all ears on that measure. So this project is about survival analysis, and that's a kind of statistical modeling for when your dependent variable is a duration or just a length of time until something happens, right? It comes from medicine for measuring how long will a patient survive after a diagnosis or something like that. In political science, we often use this for how long will a war last, how long will a peace agreement remain, how long will it take for a coalition of parties to form, things like that. So the most common model of survival data currently in use in political science is the Cox Proportional Hazards Model. And this is a great model. It's very flexible to all sorts of situations, all kinds of specifications. But it has one big problem, and that's it's unable to answer really important questions that people who are looking at survival data would be very much interested in. In particular, the important questions are, Cox proportional hazards cannot tell you how long it will take for something to happen and how much longer it would take under different conditions. So we have a few replications in our paper dealing with different subjects in political science. For each of them, there is a very obvious, important question that the Cox Proportional Hazards Model can only get at indirectly. These questions are, how much longer will it take for the U.S. Senate to confirm a federal court nominee under certain conditions, like when the opposing party in the Senate is more ideologically distant from the president? Another one is, how much longer will it take for a government to form when the parties in the coalition have a large ideological range, that they're from all across the ideological spectrum, as opposed to when the parties are very similar? Or how much longer will peace endure after a Civil War agreement when the provisions are made to reduce informational asymmetry and uncertainty? These are important questions, right? And we can only understand them indirectly and incompletely right now with this wonderful tool, the Cox Proportional Hazards Model. And so our goal is not to offer a new model. We want to use the Cox Proportional Hazard Model and all of the advantages that it has, but we want to adapt it to be able to give us direct answers to these questions. So that's our goal. A little bit of background before we talk about how we do this. So survival analysis is concerned with the distribution of lifetimes. So our dependent variable is this capital T, and it can only be positive. These values, t, represent the duration of any observation. And so we, because it's a random variable, we can define distributions. So we have a CDF, a cumulative distribution, denoted as capital F. That is the probability that a particular case will last as long as some value little t or less than that. And then the derivative of that is your failure density. And I want to point out, I'll talk about this a bit more in a little bit, that little f represents failure density. It isn't in and of itself failure probability. And it's important to keep in mind the distinction between density and probability. And I'll come back to that in a minute. So we have these functions through which we build a survival model. So we have capital F and little f, the CDF and PDF of the failure times. We also have capital S, which is a function we call the survivor function, 1 minus capital F. And this represents a probability that a case can survive a certain amount of time or longer. From these functions, we build something called the hazard rate, which is little f over capital S. That is the failure density conditioned on the survivor function, or conditional on case I surviving through time t, right? So the density of failure times at conditional on a case lasting a particular amount of time. That's the hazard rate. And this is the most important function in survival models. And this is often what we talk about when we interpret results. In particular, most commonly, results are presented in terms of the hazard ratio, which is the multiplicative change in this hazard rate for a unit increase in x. So the hazard ratio is currently the only way, and the most common way, really, that Cox proportional hazard results have been presented and interpreted in published research. Now there are two big classes of survival models. There are parametric survival models and a semi-parametric survival model. First, the parametric survival models start with an assumption about how the hazard rate is distributed over time. Maybe it's the case that hazard is highest early on, so that most of your cases will fail quick. Maybe it's a case that hazard increases over time, so that you're not likely to fail right away, but the longer you go, the more likely you are to fail, right? Some of the parametric survival models can produce statistics like expected survival time and the marginal change in expected survival time for some change in a covariate. And those are the statistics that Jeff and I are trying to calculate from the Cox Proportional Hazard Model. These parametric models that can do this are Weibull, exponential, log normal, and log logistic. Now, we have these. These models will give us the statistics we're interested in. So the question is, why don't we just use Weibull and not Cox Proportional Hazard? And the reason is these parametric models make very restrictive assumptions about the distribution of the hazard rate with respect to time. So if you are going to use the Weibull parametric model, then you have to be comfortable assuming that your hazard rate monotonically increases or monotonically decreases over time, right? So you can't ever be in a situation where hazard goes up and then down and then it goes up again, because Weibull will never be able to give you a good estimate of that. If you want to use the exponential model, you have to make an even more restrictive assumption, the assumption that your hazard is flat, that every point in time is just as hazardous as any other point in time. Log normal and log logistic make an assumption of unimodality, so that your hazard is increasing up to a point, and then thereafter your hazard is decreasing. If you're not comfortable making any of these assumptions, you cannot use the parametric survival models and expect accurate results. And so if we have this situation where the parametric survival models are misspecified, we have an alternative, and that's the Cox Proportional Hazard Model. So Cox Proportional Hazard is it's flexible, and the way it achieves this flexibility is as follows. It only considers the order of the duration times, not the intervals between them. So if one observation fails after 3 weeks and one observation fails after 3 years, the Cox Proportional Hazard Model doesn't care about weeks or years. It only cares that one observation came first and the second observation came second. It only considers the order. Because it only considers the order and it throws away the information about the actual durations themselves, we call the Cox Proportional Hazard Model a partial likelihood maximization model. And because it only considers the order, that's what gives it the ability, without getting into too much detail, that's what gives it the ability to model a general form of the hazard function. So if you're in a situation where hazard goes up and then it goes down and then it goes up again and it moves in weird ways, you can use the Cox Proportional Hazard Model, but you have to keep in mind that you are only using part of the information available to you, the order and not the actual durations. Cox Proportional Hazard Model results are usually interpreted as hazard ratios, but they cannot generate predicted durations, right? So the parametric models have this really intuitive way to understand the results. Cox Proportional Hazards does not, but CPH has hazard ratios. Now hazard ratios work like this. Here we have the hazard rate, little f over big S, and a hazard ratio tells us the following. For a 1 unit increase in x, that is, as some independent variable x goes to x plus 1, we expect this ratio, little f over big S, to be multiplied by the hazard ratio that we see in our results, that delta or whatever. So it means if delta is equal to 2, that means that the conditional failure density, that is, failure density conditional on the survivor function, is now twice as large. And so the question is, what does that really mean? It's easy to calculate. In the Cox Proportional Hazard Model, delta is just the exponentiated coefficient for the variable you're interested in. But density, even conditional density, has no substantive meaning, right? Think about a PDF. If you consider the normal distribution, standard normal distribution, the highest point on the standard normal curve occurs at a y value of 1 over the square root of 2 pi. But 1 over the square root of 2 pi isn't important, right? What's important is the area under the curve, because that gives us probability. And so while density, if density goes up, it's certainly related to the concept of failure probability increasing. It's not the same as failure probability increasing. So while we're talking about densities changing, we are missing the story about the probability of failure at any point in time. We're missing the story about how long do we really expect the duration to be. And so as a result, researchers can only really remark on 2 things when they interpret the results. First, whether the hazard rate is increasing or decreasing, and they make a statement about that looking at whether the hazard ratio is greater than 1 or less than 1. And they also can comment on whether or not this change is statistically significant. So right now we're in a situation where researchers can comment on the sign and significance, but not on the magnitude of this effect. And so we argue that hazard ratios, first of all, make it easy, too easy, to conflate conditional probability with conditional density. Now that's not exactly a problem with the model, but because the hazard ratio has this sort of vagueness built into it, it's natural for researchers to want to ascribe more meaning to it than I think it really has. And second, these hazard ratios, because of the vagueness, they really don't say anything definitive about the magnitude. They're related to magnitude, but you can't back that out yet. And so we argue that a much better result would be the predicted duration, right? So instead of a hazard ratio, we will say how long do we expect a case to survive for particular values of x, or how much longer do we expect a case to survive for a change in a particular x. Phrased this way, these quantities of interest don't conflate probability and density, and they do have an intuitive meaning that can be interpreted by a wide audience. So our goal is to give researchers a method for survival analysis that like the Cox Proportional Hazards Model, models general forms of the hazard distribution and doesn't make a restrictive assumption, but like the parametric models, can generate a predicted duration or a marginal change in duration. And so we're working on 3 ways to do this right now. We are extending the Cox Proportional Hazard Model to give us these expected durations and marginal changes. Our first approach is using a generalized additive model. And this is the approach I'm going to talk about today, just due to time constraints. But we are working on 2 alternative approaches to do the same thing. One is to use the fact that for a discrete time model, we can run a model that's isomorphic to a Cox Proportional Hazard Model as a C-log-log regression. And we're also looking at using a fully non-parametric approach that was written about by Cox originally, the person who created this methodology to begin with. Now, the generalized additive model, that's an approach that we've designed ourselves. The C-log-log and the non-parametric approaches, those are things that currently exist, although they're not used all that often. But I want to point out that even when the non-parametric and the C-log-log approaches have been used, researchers haven't extended these approaches all the way to getting expected durations and marginal changes. To our knowledge, we're the first people to actually get these statistics from a Cox Proportional Hazard Model. We're going to implement all 3 of these approaches in an R package, which we're going to call CoxED. We might consider different names, but right now we're calling it CoxED, that is Cox with expected durations. So let's talk about the GAM approach. So the GAM approach has 5 main steps. First, we're going to estimate a Cox model the way we always do. Second, we're going to generate and rank the linear predictor that we can pull from the Cox Proportional Hazard Model. Third, we're going to estimate a GAM, a generalized additive model, that fits the observed durations against the ranks that we just pulled out from the Cox Proportional Hazard Model. Fourth, we're going to use that GAM to predict out of sample expected durations and marginal effects from the GAM fit. And then fifth, we're going to repeat the process many times using bootstrapping to generate standard errors around all of these quantities. So going over the steps one at a time. Step 1, estimate a Cox model. There's nothing new here. All of the issues that a researcher has to consider when specifying a Cox model are still issues that a researcher has to consider. How do you measure your variables? How do you choose your covariates? How do you handle ties? Whether or not the proportional hazards assumption is valid, or whether you can get around it by using a time-varying covariate. And then issues like stratification. These are all things that a researcher still has to consider. Now, after building the best possible Cox Proportional Hazard Model, the following steps describe how to extend it to get better quantities of interest. So step 2 is to rank the linear predictor. Now, after we've estimated the Cox Proportional Hazard Model, then we'll have a coefficient list. We use the coefficient list to multiply the coefficients times their covariates, add that up to get a linear predictor. And then we consider the rank of the linear predictors. These are the expected ranks drawn from the Cox Proportional Hazard Model. And then we fit those against the number of, against the observed durations. So in the figure on this slide, on the x-axis we have the expected ranks drawn from the Cox Proportional Hazard Model, and on the y-axis we have observed durations. Now, this particular picture comes from one of our replications. This is from a paper by Martin and Vanberg, and what they're looking at is how long it takes parties in Western European countries to negotiate to form a government in the case where no one party has a majority. And so we have the rank, the number of bargaining days. Most of these cases were negotiated pretty quickly. You could see down here that a lot of them were under 20 days. Most of them were under 20 days. But some of them took half a year or more. So we build this scatter plot with the expected ranks and the observed durations. Step 3 is we fit a generalized additive model onto the scatter plot. So a GAM, for those of you who aren't familiar with GAMs, it's very similar to a LOS, where we're looking at local weights in order to fit a curve that contours to the shape of the data. It's not restricted to be any particular shape, like a line or a parabola or anything like that. What's different about a GAM relative to a LOS is that we can actually use a GAM to estimate confidence intervals and to estimate and to draw predictions out of sample. And so on this graph, now we have the GAM over the same scatter plot. And here we have, just to illustrate one data point and what's going on with this data point. This is the Netherlands in 1986. It had a number of parties that had to negotiate in order to form a government. It took 54 days for these parties to complete their negotiations. Our model predicts it to be 44 days. So here we have an observation that's slightly above our prediction, but like any regression, we're going to have some data points above and some data points below the line. So this is applying the GAM to that scatter plot. Step 4, we're now either going to use this curve to predict out of sample expected durations for each observation, or we're going to generate expected durations for 2 hypothetical covariate profiles in order to compute a marginal effect. When I say hypothetical covariate profiles, I mean what would it look like if a particular x of interest was low? And then what would it look like if a particular x of interest was high? And then what's the difference in expected duration as a result of going from low to high? And the way we do that is we take some variable of interest, x, and we set it to a low value for everybody, and we calculate the, or we set it to a low value for an observation, and we calculate the exponentiated linear model for that observation. And then we set the value to a high value, and then we recalculate it, and we add these 2 new data points to the rest of the data, re-rank, and then pass these new rankings to the GAM that we've already run, and then generate expected durations from that GAM, and then the difference between these 2 expected durations is our marginal effect, the change in duration time as a result of a change in this x. So here's our GAM once again. If we just draw the line, then we can now put onto this graph 2 hypothetical covariates. So let's suppose that we have an observation with a low value of x and an observation with a high value of x. And so the red line is the rank, the predicted rank from the Cox Proportional Hazard Model when that covariate x is low, and then we have the predicted rank when that covariate x is high. And so we draw those on the x-axis, and now the GAM tells us on the y-axis the expected number of bargaining days for each of the 2 covariate, or for each of the 2 observations. And then we can compute the difference on the y-axis between these. So in this picture, going from the low value of x to the high value of x resulted in 51 fewer days in negotiation. And then step 5 is we repeat the process many times. That accounts for uncertainty. So we want to get standard errors and confidence intervals on all of these quantities that we're estimating. One way to do that without making a whole bunch of parametric assumptions and distributional assumptions is to use bootstrapping and simulation. So we're going to take a large number of bootstrap samples. Each one draws with replacement from the observations that we have. We re-estimate these quantities for each bootstrap sample, and then we look in our we look at all of the values we've gotten, take the standard deviation. That's an estimate of the standard error for that quantity. So that was the GAM approach. I do have a few slides on the C-log and on the non-parametric approaches if anybody's interested. Okay, so what we've done so far for assessing the quality of our GAM approach, we've done a few simulations. So what we're trying to do is we're trying to compare Cox ED to the parametric models, exponential, Weibull, and log normal, in terms of how well each of these models returns expected durations and marginal changes in durations. We want to see if we're doing better, if we're always doing better, if we're always doing worse, or if we're sometimes doing better. And we vary the sample size. And we've got two situations that we're simulating, two data generating processes. The first situation is we are generating a totally random, often bizarre baseline hazard. I can talk, if anybody's interested, about our methodology for generating random baseline hazards, but here are 4 pictures from that. So sometimes the baseline hazard looks quite nice, even linear, but sometimes, as in this last picture, the randomly generated baseline hazard can be really wacky, all over the place. So that's our first DGP, our first situation. The second situation is we're going to draw hazard from the parametric model that's being assumed by these parametric models. So this is comparing Cox ED to Weibull on Weibull's home court, right? We're going to assume that hazard is Weibull distributed, and then compare Weibull to Cox ED. So our expectations is that when the hazard is really parametric, you're better off using a parametric model. But if the hazard is something that no parametric model will be able to model well, then Cox ED is a good option for getting these statistics. And so the way we evaluate the performance is we look at, we generate the data, right? So we know the true value of the expected durations, we know the true value of the marginal effects, and we compare each model's expected durations and expected marginal effects to the true values, and we compare them with the root mean squared error. What we see is exactly what we expect, that when we have randomly generated hazards, Cox ED outperforms the parametric models. Especially true as the sample size increases. But we also see that if we're generating hazard from a parametric function, that the parametric models are okay. And I think that's to be expected, right? If we were very confident that the Weibull model was a fit for our hazard, then we would just go ahead and use Weibull. So those are the simulations. One note is we are currently working on putting not just GAM. These are the results for the GAM approach. We're also going to put the C-log-log and the nonparametric versions of Cox ED into the simulation as well. And we're going to try to adjudicate each one against the parametric models and adjudicate them against each other. So we have 3 replications in our article. One by Martin and Vanberg on coalition government formation in Western Europe, one by Binder and Maltzman on the amount of time it takes for the Senate to confirm a judicial appointee, and one by Matz and Savin about the duration of Civil War peace agreements. Today I'm just going to talk about the Martin and Vanberg, and I've shown some of the scatter plots from that paper already. But our goal in these replications is not to not necessarily to assess, are the results valid or invalid or whatever. We would like to add to these replications. We would like to show that Cox ED helps us to understand the substantive interpretation of the results of these studies. And so the Martin and Vanberg article considers 2 independent variables, 2 key independent variables, and looks at their effect on the amount of time it takes for parties to negotiate a coalition. First of all, the ideological range of the government, that is, are parties going from like center-right to far-left, or are they all like center-left parties? And the number of parties, 2 parties, 6 parties, right? And so the idea is that both of these factors will increase the amount of time necessary to negotiate, right? And so here are a few quotes with the original interpretation. These are pretty standard ways that hazard ratios are described. It's always a challenge to write up hazard ratio results because it's density. So how do you describe it? Do you talk about, say you have 1.23, right? So you talk about 23% increase in the hazard rate. So is that the odds of government formation? Is that the probability? Is that the risk? Right? So it's not probability, and so a lot of researchers use terms that are a bit vaguer, you know, odds or risk, or just likely, generally speaking. So here is our application of Cox ED to the same model. So what we see is in comparing single party, meaning all of the parties were basically at the same spot, to a large coalition. We see really no significant difference, right? Under the single party situation, we have 19 expected bargaining days. Under a coalition, we have 23, but we don't see a significant difference between that. Now, as the number of parties in the who are negotiating increases, here we have, if we go from 2 parties to 3 parties, we expect 7 or 8 more negotiating days. If we go from 2 to 4, we're going to expect 19 more days. If we go from 1 party to 6 parties, we expect 43 more days to negotiate. And so, just a few conclusions. By stating results in that way, that as we go from one state of the world to another, we're going to expect the length of time to increase or decrease by some amount. We believe that this statistic is really what the statistic that researchers, students, policymakers actually care about. It's possible to get these statistics from parametric models, but then we would lose all of the advantages of the Cox Proportional Hazard Model, especially when the baseline hazard is, when it's not possible to make a restrictive assumption about the baseline hazard. And so Cox ED is a method for computing these expected durations while staying in that framework with all of its advantages. And so we have a few things to do. We are currently working on, we've written up the code for C-log and fully non-parametric, but we're in the process of doing all of the quality controls. We're checking, we're refining, we're debugging these things and getting our package ready. And once we have that done, then we'll be ready to complete our simulations by comparing all 3 approaches. And so thank you very much. And not sure how questions work, but I'm ready for any and all questions.
And I will now tell you how questions work. Thank you for the presentation, John. At this point, he's available to take questions from the audience. You may call in to ask a question on the air at our toll-free call-in line, 1-855-667-8287. That's 1-855-NO-STATS. You can email questions to methods.colloquium@gmail.com. Finally, you can ask a question using the GoToWebinar Ask Question box that appears on the GoToWebinar control panel. For our viewers outside the United States, we recommend using the Ask Question box to ensure that we receive your questions immediately. So, while we're waiting for some questions from the audience to come in, I'm not an expert on survival models, that's for sure, or duration models, but my understanding was that you could estimate non-parametrically, essentially via some sort of version of the Kaplan-Meier curve, a baseline hazard rate. And once you have the baseline hazard rate, you have everything you need in the Cox PH model to estimate a survival curve. And then from the survival curve, you could compute probabilities, right? So what is it that you're, I'm wondering if you can distinguish what you're doing from that approach.
Well, that essentially is the non-parametric approach. What we're adding is really the 2 additional approaches. There's a few issues with the with that Kaplan-Meier approach. First of all, it doesn't distinguish between any kind of duration in the intervals between 2 observed durations, right? So it's a step function, and so there's no way. The question is, how do you get probabilities, and then how do you take those to expected values? And so there's 0 probability. If I have a failure at 1 and a failure at 3, there's no probability of a failure at 2. but it is a valid approach, and we are developing and trying to compare it to the other two approaches. It's yeah, it is something we're looking at. Yeah. Yeah, so I'm not sure what else I can say about it until we know more about it from our simulations. One thing is that even though it's possible to do this, we haven't seen anybody do that. So we would consider it still to be a novel contribution to take that approach as far as reporting marginal changes in expected duration.
Well, I mean, I assumed that if I knew about it, that it was something that was known, because my assumption is I have no magic or special knowledge about the survival function. So are you saying that no one has ever done it, or are you saying that no one in political science is making use of that technique?
We think that no one is. We could be wrong, right? Like, you know, we've read a whole bunch of things. It just, the hazard ratio is really, really predominant. Even while this alternative approach exists, right? The C-log-log approach is also something that's out there, but in order to use that, you can only use that for discrete time. And even then, the approaches that have used C-log-log for survival models, we haven't seen one take it as far as reporting marginal changes in duration. So, yeah, we have one completely novel approach, two adapted approaches, but in any case, what we're doing is new.
I also have a question about, so you mentioned several times that the density is not a probability. But you can integrate the density over any sort of change in time to get a probability of failure in that time, right? That's what a density is.
Yes.
So if I can have access to the density, it would seem to me that I should immediately be able to have access to any probability that I want to have. So if I leap, is it fair to leap from that to saying that the exponential betas from the exponentiated betas from a Cox Proportional Hazard Model, that's telling you essentially how much the hazard rate goes up, right? That how much it's going to jump. Is that going to tell you essentially for a very small integral, right, over a region near the point, that the probability is going to increase by approximately that same ratio, right? So if my hazard ratio is 2, what it's telling me is over a small integral, I'm going to have twice the probability that something's going to happen.
I think that depends on the size of the interval, right? It's not clear to me that increasing 1 point on the density by a fixed amount, saying, you know, doubling the height of 1 point on the density, tells you anything in particular about probability other than it goes up. It would depend on the width around that in order to get area under the curve. And you only know the width around that if you can characterize the entire function, which you don't in the Cox Proportional Hazard, generally speaking. You try to circumvent that. You can back it out using the nonparametric approach we were talking about. But that is going further than I think people have gone.
What I was thinking was, so a density is obviously it's the area under the curve. The probability at a particular point is the limit of that integral as it goes to 0, right? The boundaries get closer and closer to the essentially if you were yeah, so that's what's going on there, but we don't want an infinitesimally small range, but we could imagine there being a relatively small range, right? So I don't know what your unit is for time, but if it's, you know, months or years, you could imagine maybe just in the next 1 year, right?
So if we're in continuous time, then the very question of the probability of failure at a particular time, it's zero because we're dealing with a continuous random variable. Even in the limit, it's going to be zero.
Right.
And for a very small interval, it's going to be a very small probability.
But you think of there, sort of what's the smallest meaningful unit of time, like so failure in the next year. It seems to me that the hazard ratio is going to be an approximation of how much that probability increases. Now, it won't be exact. That's because the you're not taking the integral under the PDF. You're essentially calculating the change in height right at that point. So necessarily, there's going to be some approximation loss there. But it should be pretty close, right? How much better are we doing by sort of killing the details?
I think it depends on the full shape of the density, right? If we have a very very narrow density, then I think that's true. I mean, if the interval contains if the integral contains most of the area anyway. I don't want to say something that's not true. I'm just trying to imagine this as you're asking. It's so suppose a very small interval and the relationship between changes in density and changes in probability. It's got to depend on the proportion of the area that existed in that interval prior to manipulating an X.
Well, you imagine the shape of the PDF, right? And I mean, they're usually bell-shaped, right? So imagine you have a bell-shaped PDF, and what I'm doing is what I want to do is I want to integrate a section of that curve, right? And I'm computing what I'm computing is the change in the height of the curve at a particular point, right? That's attributable to some variable. That's what the hazard ratio is telling me. Right? I'm right so far, right? And so what I'm doing is I'm essentially asking, how much would I expect probability to go up? Well, imagine taking a sort of a rectangular slice of that curve that's centered on the point where I'm calculating it. So in other words, imagine a sort of a small integral over that point. And then what I want to calculate is how much does that integral change as I go from whatever I was to wherever I'm going to be.
I mean, it's still equating changes in height to changes in area. And
it's approximating it. That's what I'm asking is how good is the approximation?
I don't know, but I think that it's a bit of a we're trying to avoid having to make that approximation, right? By taking this, first of all, while probability of failure within a particular range of times, that's interesting. I would argue that's more interesting than the hazard ratio. I think more interesting than that is expected duration and change in expected duration. So it's not estimating probability in a region, which would require assumptions about what the interval should be and how good an approximation is, which ought to be, I think, context dependent. Instead, it's estimating this moment, this really important moment.
You know, it seems to me that either, no matter what you're going to do, because the Cox PH model is designed to not be dependent on this baseline rate, anything you're going to do is going to have to try to recover that rate somehow, either through some mechanism. And it's an open question to me whether you're going to lose more by approximating. So sticking with the change in probability as the estimate of interest for a moment here, it's an open question to me whether you're going to lose more by trying to approximate the estimate by not imputing the baseline hazard rate, but then estimating essentially using the change in height as an approximation to change in area, versus what you're going to lose by trying to initiate an estimation of the baseline hazard rate and then use that to compute a more, it's a theoretically more satisfying answer because you're actually computing the right probabilities, but you've introduced a possible source of estimation error because now you're estimating something you weren't estimating before. And just intuitionally, I would think sometimes you're going to be in one situation where it's better, and sometimes you're going to be in one situation where it's worse, and there might be some guidance about when you would have to worry about that.
Well, I think we're going to have an answer for you, because we are in the process of comparing the three approaches, the GAM, the C-log-log, and the nonparametric approaches in one large simulation. I'd say that in order to get expected durations from the nonparametric cumulative baseline hazard that Cox originally proposed, you have to compute probability of failure at all of the times that are observed. It has issues, right? Like that it's a step function, but still, you estimate these probabilities, and then you use those probabilities to get the expected value. So in order to compare apples to apples, right, it's to compare an expected value to an expected value. So we'll have an answer on that very thing soon.
I want to ask another question. So this is about the way that you estimate the baseline hazard. So if you had just asked me before this talk, again, not being an expert on survival models, but if you just asked me point blank, I want to estimate a baseline hazard rate or a baseline survival function, and I want to do it nonparametrically, but I don't like the fact that there are steps. What I would have said was something like, okay, maybe we can smooth that, right? We can take the Kaplan-Meier, which is jagged, and we can count every point, every step as a point, so to speak, and then use Loess or local linear or something to smooth that out. Sure. And that should be pretty good. And I thought that's where you were going to go, but if I interpreted your talk, you went somewhere else.
If the goal was to approximate baseline hazard, then yeah, I think that would be a very interesting approach to consider, a very promising one. But that's not our goal, right? We're trying to speak to questions of how long does something last and how much longer would it last under different conditions. We believe that those questions are more interesting from a substantive perspective and more accessible to a wide audience. We can get those from the parametric models, but the question is, how do we get those statistics? That's the goal. That was originally the goal. And we don't want to stop at baseline hazard. Even if we smoothed out the baseline hazard, the goal would still be getting to those statistics.
Well, but if I had the baseline hazard, then I would have everything I need to compute directly from the Cox PH all the duration statistics and probability statistics that you wanted, though, right?
If you have the baseline hazard, you could integrate it to get cumulative hazard, and then you could exponentiate it to get the survivor function, and then 1 minus to get the failure CDF, differentiate to get the failure PDF.
Doing all that numerically, I assume, or at least most of it.
Do all that numerically, right? And then once you have, if you're confident that you have a good estimate of the failure PDF, then you could get moments from it.
That's what I thought you were. I mean, I'm going to now make a shocking admission that I didn't read your paper before the talk today. I thought, but based on what you had told me, and we had talked about this, and I read your abstract, I thought that's what you were going to do. And so I'm really curious as to why you think your approach is going to give better results than this sort of little approach that we sketched out, which is based really on what I would consider to be the structure of the model.
Well, again, we're considering that. So the nonparametric option. So the reason why I suspect it's not going to end up being, in our preliminary results, it's not quite as good. It's because it's numeric approximation upon numeric approximation upon numeric approximation, right? At some point, it's just too many approximations in a row. And so the GAM approach, it's you take the expected ranks, you map them onto observed durations. It's a one-step thing in addition to the Cox model itself.
So if this other alternative was going to work, you'd have to find a way you wouldn't want to do 5 calculations in a row. You'd want to skip right to the last one as best you could.
you could do that if you had, if you knew what the density was, right? But you don't. That's the whole point.
Yeah, we're estimating that. We have to. Yeah. That's interesting. Okay. Well, I think I think we've taken up enough of your time, so I want to thank you for giving a very interesting talk. I really enjoyed it. I'm not an expert in this area, so it's cool when I get to learn new things. I'll be looking forward to the seeing your paper in print. Next week, tune in at noon Eastern, 11 Central for a presentation by Dan Hopkins of the University of Pennsylvania. His talk will be entitled Learning More from Conjoint Experiments Through a Doubly Randomized Design. You can go to our website, www.methods-colloquium.com, for more details. John, thanks very much for being here this week.
Thank you, Justin, and thank you, Internet.
Yeah. See you next time.